Hello, this is our interim presentation for the analysis and redesign of the trolley cart, presented by the members of Team 2. Our product is a general-purpose trolley-style cart. It's made to transport items of various sizes and weights. Its features include 2 trays, ergonomic steering grips, fixed wheels, as well as collapsible tubes for ease of storage. Our anticipated production volume is 201,000 units per year. Here's a simple exploded view of our assembly with all parts excluding fasteners. Our customer base consists of 2 customers. Our primary customer will be the office or corporate setting, machine shop workers, and food industry workers. So these industries all have something in common. They have large workspaces that require transporting of items from one side to another on a daily basis, whether that's office supplies, food supplies, or tools. Catering a product to these industries, which are globally present, would both be helpful to them as well as yield a successful product. Our secondary customer base will be the film production, industry, and media companies. The trolley cart lends itself to customization, which allows for addition of attachments that can be very industry specific. So with this in mind, film and media industries can utilize these types of carts for transporting expensive equipment, such as computers, cameras, boom mics, and things of that nature, as well as actually using the cart to film.
Here is our design for manual assembly. The original assembly of our cart takes about 2,195 seconds. The assembly after redesign takes about 1,475 seconds. We redesigned both a module and platform part to improve manual assembly efficiency from 1.4% to 2%. The improvements of our module part include the removal of 5N/16 flathead screws to reduce fasteners, the removal of bracket bases to reduce parts, and the addition of a cylindrical extrusion at the bottom of the part to provide a locating feature. The improvements of our platform part include the removal of M8/16 screws to reduce fasteners, the removal of M8 nuts to reduce fasteners, the removal of lower angle brackets to reduce parts, and the redesigning for insertion by sliding onto the corner of our shelf instead of attaching it via fasteners.
Shelf. For the platform, we selected the top shelf of the cart, and the 3 small lightweight parts are the flat bracket, the angle bracket, and the butterfly latch. Here are the handling and insertion cost analysis of the original subassembly versus the subassembly post DfA. A couple of key things to point out are the significant reduction of number of parts, as well as the reduction in total assembly cost. The first redesigned part is the flat bracket. The new flat bracket has a shorter length for easier handling and feeding, a reduced number of fasteners, the 4 corner bosses for easier alignment and insertion, as well as preventing potential overlapping during feeding. The top shelf has also been modified accordingly in order to adapt the new flat bracket. The second part is the angle bracket. The new angle bracket has an integrated lip to eliminate the need for all fasteners. The new part is also installed vertically from above, which reduces the workhead cost while maintaining its functionality. Lastly, we have the butterfly latch. The new latch has a reduced number of fasteners, and the added tab on the top shelf also allows the part to be installed vertically from above. Next, we have the process selection for the lower support tube mount. The most significant feature of the support tube mount is the upper cylinder, because this is what allows the support tube to maintain structure as stated in the FCMM to the lower shelf. We chose a tolerance of plus or minus 0.1 millimeters because it wasn't necessary to go any finer without increasing the cost. Next, we have the process selection for the angle bracket. The most significant feature of the angle bracket is the integrated lip, which eliminates the need for all fasteners. We chose a tolerance for this part of plus or minus 0.5 millimeters because similarly, it wasn't necessary to be any finer without increasing the cost. Here are the charts for the process selection. For the lower support tube mount, we chose aluminum for the material because it is relatively strong, lightweight, and inexpensive. For the mode of manufacturing, we chose machining due to its geometry. For the angle bracket, we chose to injection mold this part due to its geometry with high density polyethylene because the material is relatively strong, lightweight, and inexpensive.
For our first design for assembly product, the bracket, we decided to injection mold it as our primary manufacturing process. Our pre-DFM cost was 12 cents per part as determined by analytical methods. Through DfM Pro, we determined that increasing core width, installing a draft angle, and increasing uniformity were primary redesign paths. As depicted on the right, we used DfM2, DfM3, and DfM4 to improve our design by installing a draft angle, maintaining uniform thickness, and installing smooth corners. Our post-DfM cost was 11 cents per part, largely due to the heightened cooling times, or the decreased cooling times, as well as the greater ejectability of the part. For our second design for assembly part, the bottom support, we decided to manufacture it through machining. Our total cost for our pre-DfM part was $20.92 per part. Through DfM Pro, we decided to target tooling consolidation and wall height as main redesign factors. As depicted on the right, we used DfM3, DfM10, and DfM15 by consolidating the fillet to a chamfer, by decreasing the milling height, and standardizing the hole for M4 screws. Our post-DfM cost was $20.24 per part. Comparing our machine manufacturing method to hubs, we see that hubs has a much lower cost per part compared to our analytical methods. This could be due to a number of things, such as the use of different materials, as well as different stock prices. When designing for a product service system, we wanted to please our customer while providing high quality service by offering maintenance plans, by offering membership plans that give the customers greater perks for and upgraded versions of the car in the future. And we also want to collect outdated and unusable products for recycling. These policies will yield better customer relations while also benefiting us and the environment. Conclusion. For both the automated and manual assembly, the decrease in time per assembly was seen. For DfMA, we saw 88 less parts being used and 719 seconds per assembly being saved. For DfAA, we saw 52 less parts being installed and 69 seconds being saved. The redesign for our selected machine part for DfM decreased our price from $133 to $124. This results in a $72,000 saving on a yearly basis. We believe our design is an optimized version of the Frieza because it lends itself to customization. We believe that other versions can still be made for different industries. However, the design has a lot less to optimize. Our design has plenty of fasteners and joining parts that could be redesigned to save more money. If we could do this redesign again, we would like to diversify our product more, enable reach into more industries, and also streamline our design more to take less time for assembly by redesigning the amount of parts. Ideally, this would happen through intense FCMM analysis to really see what is and isn't necessary for our goal function. Thank you.